Hello, very good morning. So, in this class, let us continue with the thermal transducers. So, there are basically three types of thermal transducers. One is called as RTD, it is called as resistance temperature detector, and second one is called as thermistor, and the third one is called the thermocouple transducer. So, both all the three types of transducer, so they depend on the temperature. So, if temperature is changing, the active element in that, which is called as the resistance, it is going to change. So, now in the first type we will see what is meant by the resistance temperature detector. It is called as RTD. So, here in figure A, so I have shown the basic construction of an RTD. So, it contains a glass shield, it is called as a glass shield, we call it as glass protective sheath. Inside that there will be a resistive element, so connected, so in a zigzag fashion like this. So, it is called as resistive sensing element. So, here, so this resistance is going to sense the temperature. So, for that, so we have given a connecting leads. So, these leads is connected to a temperature varying system. So, these leads will sense the temperature, and when the temperature is sensed, the resistance of this particular material is going to change. So, now the equivalent circuit of this RTD is shown here. So, it is called as RC1 and RC2. So, what is this RC1 and RC2 are? The resistance of the connecting leads. Along with we have got one is known as the source resistance. Source resistance is nothing but the wire inside this one is called as the resistance, which is called as the source wire. So, that resistance it is going to change. So, the equivalent circuit of this one is as shown here. Okay. So, now see, let us see, so what is the basic principle of an RTD and how the resistance is going to change with respect to temperature. So, for that, so I have a basic equation like this. Let us assume that the initial temperature of this particular sensing material is R1. So, as you know that resistance is measured in terms of ohms. So, therefore, the initial resistance of the sensing material is R1 ohms. So, now as the temperature changes, the resistance is also changing. So, I have called this as delta R. So, change in the resistance is called as delta R. So, with the change in the temperature delta T. So, now what is the temperature we have to consider for the change in temperature? Usually, so we take 0 degree to 20 degree as the normal temperature, 0 to 20 degree as the normal temperature. Once the sensing element is heated, so the temperature is going to rise above 20 degrees centigrade. So, that temperature change we are calling it as delta T. Okay. So, initially the resistance is R1. So, when we heat the sensing wire, the changing resistance is delta R, and also the change in the resistance is delta T. So, now the change in resistance is represented like this: delta R is equal to initial resistance into alpha into delta T. What is this alpha? It is called as the temperature coefficient. So, usually the sensing material here what we use is a pure metal, and all metals will have positive temperature coefficient. So, this alpha represents the temperature coefficient, and delta T is the change in the temperature. Now, the new resistance after heating, the resistance will change. That new resistance is given by R1 plus delta R. Initial resistance at 0 to 20 degree, this temperature plus delta R, so greater than 20 degree. So, this is the resistance with respect to temperature change. So, now, so I will substitute for delta R in this from this equation. So, therefore, it becomes R1 plus R1 into alpha delta T. So, taking R1 common, so I will get 1 plus alpha into delta T. So, this is what is the working principle of an RTD. The change in the resistance is given by initial resistance into 1 plus the temperature coefficient and the change in the temperature. So, this is the basic working principle of any temperature transducer. So, here, we are calculating the temperature in terms of the change in resistance. So, now with this principle, here we have got an equivalent circuit in the form of a Wheatstone bridge. So, where this circuit is connected as one of the arms of the Wheatstone bridge. As you know that in Wheatstone bridge we have got 4 arms, R1, R2, R3 and R4. When the resistance are equal, the bridge is said to be balanced, and the meter reading in this one, it may be current reading or it may be voltage reading, it will be 0. So, now this equivalent resistance circuit is connected here to the 4th arm. So, this lead resistance, the wire, it is RC1, and this is the source resistance, and this is again the lead resistance RC2. So, basically when temperature is changing, the resistance of this is going to change. So, therefore, I am representing it as the variable resistance. So, now initially we will assume that the temperature is in room condition, that is 0 to 20 degree. So, in that condition this Wheatstone bridge is said to be balanced, and you know that the standard formula is R1 by R2 is equal to, so I will take this as R4 and RS, so I will take it as R4 and by RS. So, this is what the condition. Okay. So, when the bridge is balanced, the resistance are equal. Once the temperature changes above 20 degree, so there will be change in the resistance, that is delta R. So, that is represented here. So, RS is going to change, then the bridge is said to be unbalanced, and the meter reading will show the proportional voltage drop across the bridge. So, that is given by the voltage or current. So, therefore, I can say that the change in the resistance is proportional to voltage. So, change in the resistance is proportional to voltage. Hence, the change in the temperature is proportional to the voltage change across the resistance of this particular RTD. So, this is what the working principle of a typical resistance temperature detector. So, usually this RTDs are used to measure the temperature from say 20 degrees to 250 degrees or 300 degrees. So, it can give a linear output. So, we say it is linear. Linear means what? So, output of this Wheatstone bridge, it will be linear, so for certain voltage range. Okay. So, this is what the resistance temperature detector is. So, the next type of thermal transducer is called as a thermistor. In this thermistor, there are two terms, one is temperature and resistance. So, temperature plus resistance is called as thermistor. So, it means that whenever there is a change in temperature, resistance is also going to change. So, that is what the basic principle of a thermistor. So, this is the construction of a thermistor. So, thermistor are basically manufactured using metal oxides. So, metal oxides, they are very sensitive to temperature. So, they are used for the construction of a thermistor. So, the thermistor is usually manufactured in the form of a disc. So, here I have written. So, it is manufactured as in the form of a disc or beads or probes or disc or a washer. So, this is what the construction. So, this is how the thermistor look like. So, now I have taken in the form of a disc here, in which two metal contacts are derived from this baked metal oxide. Okay. So, now here this type of disc thermistors can measure temperature up to 200 degrees centigrade, okay, and their sensitivity is very high. Since metal oxides are very sensitive to temperature, a small change in the temperature will be reflected in the change in the resistance. So, that is why thermistors are used in some critical temperature applications where small temperature change should also be considered for the measurement. Okay. So, usually the thermistors are the negative they work on negative temperature coefficient. So, that means they have got large resistance at small temperature, and when temperature is very high, the resistance decreases. So, this is a typical graph of a thermistor where at the small temperature you are seeing here it is minus 20 degree. In the negative temperature resistance is very high. So, as the temperature increases in the forward direction, so maximum I have taken here is 60 degree. For the 60 degree resistance has come down. So, this is called as negative temperature coefficient. All thermistors are negative temperature coefficient materials. Okay. So, now here I have taken 2 points on this graph. So, one is at exactly 0 degrees and second one at 60 degrees. At 0 degree we call it as the standard temperature. Usually the resistance of a typical disc type thermistor will have 1.5 kilo ohms, and at 60 degrees so the resistance drops. So, it is around 70 ohms. So, now as you can see here, so by the Ohm's law, if you take V is equal to IR, and if I want to measure voltage in terms of the change in resistance, we know that so V is proportional to I, and so if I take the proportionality, V is equal to IR. So, now here if I apply this principle to this thermistor, so here resistance is changing with respect to temperature, right. So, that means so if resistance is changing, so voltage is also changing across the thermistor. Okay. So, now here so I have taken a small circuit, so where so we can measure the temperature in terms of resistance or in terms of voltage. So, now you know that this is a small inverting amplifier constructed using a op amp. So, you know that standard op amp is OP07 or it can be mu A741. So, there are standard op amps available, so through which so we can measure temperature in terms of change in resistance. So, you know that in a inverting amplifier, if you want to calculate the output voltage V0, it is given by minus RF divided by R1 into V1. So, V1 or it may be Vi. So, what is this Vi? The input voltage. So, now here this circuit, here I have taken the input resistance as typically 27 kilo ohms, and this RT when it is going to change, so that feedback resistance will come. So, RF by R1, and we always take this to be standard 1 volt because I should get voltage V0 so proportional to RF by R1. So, that is my intention. So, that is why we have considered here it as 1 volt. Okay. So, typically, so in a standard circuits Vi is considered to be 1 volt because so this V0 should be always proportional to change in resistance. If you see here RF, so I can replace by RT. So, where RT is the thermistor resistance. The thermistor resistance is going to change with respect to temperature. When RT changes, this value is going to change. So, therefore, I am going to get the output in terms of change in the resistance. So, this is how a typical thermal transistor, that is thermistor, works. Okay. So, next we will go for the next type of transducers. They are called as optoelectronic transducers. So now here there are two words, one is opto and then there is another word is called as electronic. So opto means light. So these transducer, they work on the light principle. Example, you know that solar cells, when light falls on a solar cell, equivalent electrical output is obtained. So that is the basic principle of a optoelectronic transducers. So the optoelectronic transducers are basically classified as two types. One is called as photoconductive cell and second one is called as photovoltaic cell. What is this photoconductive means? So here, so there is, whenever light falls on a material, so there is a change in the current, so that we call it as photoconductive. Similarly, when light falls on a material, so where voltage is going to change, so we call it as photovoltaic cell. Okay. So now we will see what is this photoconductive cell. So there are some materials, basically semiconductor materials known as cadmium sulfide, it is abbreviated as CDS, or cadmium selenide, CDSE. So these materials, on these materials, when light strikes the material's surface, they provide energy to the electrons. So electrons inside these materials. When electrons get sufficient energy, so the free electrons and holes are created. So when light falls on these materials called as cadmium sulfide or cadmium selenide, so electrons, free electrons will get liberated and they get energized, and so they start working, they start moving inside this material and current starts flowing. So as you know that when current is flowing, resistance should decrease. So that's what it says, when light striking the material surface, so it can provide energy to electrons. So thus free electrons and holes are created within the material. So when the charge carriers are created inside the material, it reduces the resistance. Reducing the resistance, this is known as photoconductive effect. So in simple words, so whenever the light strikes on these materials, so free electrons will get liberated and they start flowing, so the current is produced, so that is known as photoconductive effect, and so that current is called as photoelectric current. Okay. So now this is a typical graph showing the variation of resistance with respect to light intensity. So we know that, so whenever the light is falling on a material, it gets dispersed like this. So we call it as a divergent rays. So now here if we want to calculate the light intensity falling on the material, so it is given by a simple formula. So EA, we call it as illumination intensity, is equal to phi of S divided by 4 pi square. Okay. So this is what the typical formula is. The illumination intensity is equal to phi of S. What is this phi? So it is the flux. So it is measured in terms of lumens. So phi S divided by the surface area. So I will consider the light coming out of the material as a small sphere, and so the intensity is measured in terms of lumens per meter square. So therefore we have taken phi S by 4 pi r square. So this is what is the basic principle of any photovoltaic cells or any optoelectronic transducers. Okay. So now with this intensity as input, so we are going to measure what is the equivalent output we are getting in terms of luminous intensity. And we know that luminous intensity is measured in terms of a unit called as lux. So, this is a typical graph showing what is the variation of lumen with respect to resistance. So, as you see here, whenever the intensity is very less, the resistance is very high. So, here the intensity is 1 lumen, so the resistance is 100K. So, whenever the intensity drops, whenever the intensity is high, resistance is dropping. So, this is what the typical graph of a photoelectronic transducer. Now, how to measure the optoelectronic effect in terms of a circuit? So, for that, we have a simple circuit. It is called as a Schmitt trigger circuit. So, what is meant by Schmitt trigger means? A Schmitt trigger is a circuit, so in which the output voltage it starts varying. It will be varying, so with respect to some threshold values. So, this positive value is called as UTP, it is called as upper threshold value, and the negative value is called as LTP, it is called as lower threshold values. The output of a typical Schmitt trigger, it will be switching from UTP to LTP levels. So, this is a simple circuit, so where we are going to measure the UTP and LTP levels. Okay. So, now here the photoelectronic transducer, so which is called as the resistance here RC, it is connected, so in the form of a voltage divider. So, here RC represents the photoconductive resistance, and R1 it is the resistance connected to the negative voltage, and the voltage across these two is connected to the inverting terminal of the op amp, and this is R2 and R3, it provides the gain. Okay. So, now here it works on two conditions. So, this is the condition number 1. So, we will see what is this condition. When RC is less, so RC is less means what? So, as you can see here, when the resistance is less, see here I am showing here, so it is very 300, see this is very small resistance. So, whenever there is a small resistance, illumination is high. So, that is why I have written when RC is less, that means whenever illumination is high. Okay. So, now the voltage across R1, so this voltage we call it as VR1, it will be very high voltage. So, therefore, the output is low, the output is higher than the UTP. So, I have written here. So, whenever this voltage across this resistance R1, so it is very high, so the output it will be above the UTP level. So, therefore, the output will be low, V0 is low, output of the voltage, that is op amp, is low. So, this is for the first condition. So, now coming to the second condition, when VR1 is less, so it is the opposite of that. So, that is when RC is less illuminated means what? So, when the resistance is illuminated less means I will take this condition. So, here I have considered it is to be maximum illumination. So, here I am considered to be the less illumination. Whenever there is a less illumination, naturally the resistance should be high. So, now whenever RC is less illuminated, so that is here the voltage across VR1, so it will be lesser than the lower threshold value. It is called as less than LTP. So, whenever that is the condition, so output is high. So, that is what. So, in a typical optoelectronic transducer circuit, always the output will be switching from high level to low level. So, we call it as pulse output. So, this is the typical output of a photoconductive cell circuit. So, whenever illumination is high, so it will be low, illumination is less, output is high. So, this is a simple circuit for measuring the illumination in terms of voltage, and that circuit is called as Schmitt trigger circuit, and it can be constructed using the op-amp MUA741. Okay. So, this is what the optoelectronic transducer is. Okay. Now, the second type of optoelectronic transducer, they are called as photovoltaic cell. So, let us see how this photovoltaic cell, or also called as photodiodes, works. Okay. So, now let us see this figure. So, this is a typical PN junction diode. So, we call it as PN junction diode. So, you all know that. So, always diode works in only one direction, so that is in the forward direction. But whenever a diode is reverse biased, that is the positive P type of the material is connected to negative and N type is connected to positive, and that is called as reverse bias condition. Whenever a PN junction is reverse biased, so there is a small electron flow that is called as reverse current IR. So, this reverse current IR, it flows because there is a temperature inside this. It is called as thermally generated electron and holes. So, due to the reverse current here at the depletion region, so there will be a small current that is flowing. It is called as a reverse current, and this reverse current is flowing because of some temperature effect inside the junction. So, that is called as reverse saturation current. But whenever we forward bias the diode, so the ordinary current we call it as IE. So, that is the forward current, it flows from P type to N type. But here we are interested only in the reverse condition. So, whenever it is reverse biased, so therefore here, so the electrons, so they will get thermally, the electrons and hole, they get thermally charged and it start flowing in the reverse direction, and that is called as reverse saturation current. So, that principle is used. So, now here, so instead of connecting a battery, if a light source is made to fall on the depletion region, if a light source is made to fall on the depletion region or the contacts between P type and N type in that region, what happens? So, same action is going to produce. So, this temperature from the light source, it is going to excite the electrons inside the N type material. So, those electrons excited will start flowing in the reverse direction, and that is the reverse current that is being produced due to the light effect, Once again, so if you consider only ordinary PN junction, you have to excite that with a source voltage E, and if you connect a source voltage in the reverse direction, the current flowing here is called as the reverse saturation current. So, in the same way, if you remove this source voltage and if light energy is made to fall on this, the same reverse current starts flowing. So, that is with respect to the incident light on this material, and this principle is called as photovoltaic cell. So, as you know that, so in a solar cell, when the light from the sun, it falls on that, it produces a small current, and that current is called as photovoltaic current. So, let us see what is this photodiode principle, and such type of diodes, which work on the photo effect are called as photodiodes. So there are two types of diodes. One is called as PN junction diode, it is called as ordinary diode. So ordinary diode, it has to work with a voltage source, and you know that if you give 0.7 volts for a silicon diode, it starts working, and if the voltage is less than 0.7 volts, so that diode cannot work. And another type of diode is there, that is called as photodiode. So for that photodiode, if light is made to incident on the surface of the diode, so a small reverse current starts flowing, and that is called as photodiode current. Okay. So now let us see what is this photodiode principle. So the electron hole pairs are generated by the incident light energy. So that means in a photodiode, if light is made to fall on the surface of the diode, so it thermally generates the electron and hole pair, and so the minority charge carriers so are swept across the junction. That means here as in the figure you are seeing, so the minority means it is the carriers which are less in number, so that starts flowing across the junction, creating a reverse current flow. It flows in the reverse direction. So when it starts flowing, so here increasing the start flowing. Okay, so this is what the photodiode principle. If you further increase the light intensity, if the light intensity is further increased, then increasing the junction illumination increases the reverse current. So that means here the reverse current flowing inside the photodiode is proportional to the light incident on the surface of the diode. If the intensity is less, so the reverse current is less. If the intensity is more, the reverse current is more. So increasing the junction illumination increases the reverse current. Such diodes designed to be sensitive to illumination and are called as photodiodes. So diodes which works on light principle are called as photodiodes. So usually, so photodiodes works in the reverse bias condition. So this is the second type of optoelectronic transducer. First type we have seen, it is photoconductive transducer, and this is photovoltaic cell, and this is a photovoltaic cell, and it works in the photovoltaic mode. It is in the voltage mode. Okay. The last type of transducer, that is called as a piezoelectric transducer. So now what is this piezoelectric effect, we will see. So the piezoelectric effect says, whenever there is a mechanical stress applied on some material like quartz, okay, it generates equivalent electrical output. So I repeat, so whenever a mechanical stress is applied on some piezoelectric material like quartz, it generates equivalent output voltage in the form of voltage or current. So now that is called as piezoelectric effect. So mechanical stress is converted to equivalent voltage output. Okay. So now on the other hand, so if this piezoelectric bar, you are seeing it as a piezoelectric crystal arranged in the form of a piezoelectric bar, is excited by an AC voltage. If you excite the piezoelectric bar of say length L, so by an AC source, it starts vibrating. That vibrating also produces mechanical stress on that, and that stress, so it is converted to equivalent voltage. So these two methods are called as piezoelectric method. So now what exactly we are going to measure here? So the mechanical stress on the piezoelectric crystal is measured in terms of voltage. We want to measure what is the output across the piezoelectric crystal when a mechanical stress is applied on that. So, that is called as voltage in terms of mechanical stress. How to measure? So, for that we use the basic equation like this. So, now, this piezoelectric crystal, so it is in the form of, it has the charges distribution like this, positive charges on the top surface of the crystal and negative charges like this. So, now you know that the charge is always expressed in terms of the value called as Q is equal to dF. What is this D? So, D is called as the charge sensitivity and F is called as the force. Now, if you apply the force on this, so it is going to generate a charge. So, the force is applied in the top to bottom like this, bottom direction like this, and the charge is generated, and that is called as Q. And what is the unit of this? It is expressed in terms of Coulomb per Newton. So, why Newton is required? Because we have to apply force, is it not? So when you apply some mechanical force on that, it is going to generate the charge, that is called as Q. But you know that the basic formula for charge is, so it is given by Q is equal to C into V. What is this Q is equal to CV? So, in the PU class only you have come across this equation. What is Q equal CV? So, Q is equal to, what is C? It is capacitance into voltage. Okay. So, this is the basic equation of a charge. So, that equation I am going to use here. So, Q is equal to CT into V naught. What is this V naught? So, V naught is the final output voltage, so produced, so when the piezoelectric crystal is vibrated or piezoelectric crystal is mechanically stressed. So, that is given by this equation, Q is equal to CT into V naught, where the CT is called as the transducer capacitance. So, it depends on the length of this one and the width of that one. So, all these matters. So, that is why it is known as the transducer capacitance. But we know that what is the equation of a parallel plate capacitor? Why parallel plate? Because you are seeing that positive charges are arranged like this and negative charges are arranged like this. It is in the form of a parallel plate capacitance. So, therefore, this CT is equal to epsilon T into epsilon naught into A divided by T. What is this epsilon naught? Epsilon naught is called as permittivity of free space. So, it is a standard capacitance and standard value, permittivity of free space. What is this epsilon T? It is called as dielectric permittivity. So, dielectric permittivity, it depends on material to material. For a quartz, so we have got some standard value. So, that is what is this epsilon naught, epsilon T is. And what is this A? A is called the area of this piezoelectric crystal. And then what is this T? T is the thickness. So, this is the thickness. So, all these put together we can calculate the transducer capacitance. Okay. So, now what is that we are interested? So, whenever it is vibrated or whenever it is stressed, what is the equivalent voltage we are getting? So, that is given by this equation. I am just using this equation, Q equals CT into V naught. So, therefore, V naught is equal to Q by CT. And I will substitute for Q the first equation. What is this first equation? D into F. What is this D? Is the charge sensitivity into force. So, D into F, and for this CT I will substitute this standard equation of a parallel plate capacitor. So, if you substitute here, so I will get two another important factors. that is one which is called as P, that is called as pressure. So pressure is equal to force by area. So we all know that by Pascal law it says that pressure is force per unit area. So there is a factor called F is there and a factor A is there. I will take that F by A and I will call it as the pressure. So that means how much pressure is being applied on the piezoelectric crystal, so that much the charge is going to get accumulated. Okay, so that is given by F by A and is called as pressure. And similarly there is another factor is there, that is called as voltage sensitivity, and it is represented as G, that is given by this equation D divided by epsilon T into epsilon naught. And since T is in the numerator, in the denominator, it goes up. So therefore finally the voltage across the piezoelectric crystal can be calculated using the formula G into T into P, that is V naught is equal to voltage sensitivity into pressure into thickness. So this is what the equation says always. So we can calculate voltage in terms of voltage sensitivity of the piezoelectric crystal into the pressure applied on the crystal and the thickness of the crystal. So this is what is called as piezoelectric transducer.